Welcome back to another episode of Mr. Hawkins' geometry class. Hopefully you enjoyed the opening video about what we're going to look at, and that is inscribed angles. Objective for today is to be able to identify and use properties of inscribed angles. So down here, kind of have a picture of what I'm talking about. Again, I kind of introduced inscribed angles by referring to something that you're familiar with, and that's the concept of a central angle. Basically, a central angle is an angle between two radii. So again, this is the central angle right here. Its vertex is at the center. Central angle. So then in the video, I introduced the concept of an inscribed angle. Inscribed angle is basically an angle between two chords where the intersection is on the circle. So if I put the intersection of the circle right here, there's one chord, there's the other chord. So this is your inscribed angle. So remember that a central angle and an inscribed angle both make what's called an intercepted arc. So that would be this guy right here. This is your intercepted arc. Not sure why they call it intercepted, but so intercepted arc. And intercepted arc, that's the arc made by an angle. Then in the video, I kind of showed you what the inscribed angle theorem was. Again, the inscribed angle, you'll notice, is much smaller than the central angle that makes the same arc. So they're not going to be the same measurement. This is going to be smaller, and it's exactly half as big as this central angle. So the inscribed angle theorem, you can think of it in two ways. You can say the inscribed angle, I'll do that in a different color. The inscribed angle. The inscribed angle is always half of the intercepted arc. Or you could think of it another way. You could say the intercepted arc is always twice the inscribed angle. So it depends on how you look at it. But we'll be using those properties today, in that theorem today, which has a couple spin-offs on it, which are called corollaries. In any event, you'll see here is an example. Well, this is kind of like a formal definition of your inscribed angle theorem. Again, the vertex is on the circle, and it's always half of the arc it makes. So here you can see the inscribed angle is 61 degrees, and the arc is exactly double that at 122 degrees. So that's what I just went over. Important corollaries. Corollaries, if you remember, we've done them a while ago. These are kind of spin-offs of a theorem. They're true as the result of a theorem. And the theorem is the inscribed angle theorem. So down here, these make sense. It says two inscribed angles that intercept the same arc. So let's see. Here is one inscribed angle. And the arc it makes is right here. The second inscribed angle that makes that, I'll draw it over here. So now these angles here and here are both making the same arc. They're both inscribed angles. They're going to follow the inscribed angle theorem. So they're both going to be half of that measurement, which means they're going to be congruent. So two inscribed angles that make the same arc are always congruent. So for instance, if this was like a 40-degree arc, both of these would have to be 20 degrees. So that is one corollary. Another corollary talks about an inscribed angle that makes a semicircle. Well, if I have a semicircle, this would be like a diameter through here. My center's right there. So if you have an inscribed angle that makes a semicircle, and I use the inscribed angle theorem, well, inscribed angles are always half the arc. Well, if the arc is a 180-degree semicircle, and the angle has to be half of that, that means this has got to be a 90-degree angle, which means if you have an inscribed angle that makes a semicircle, it's always going to be a right angle. That's because its arc is 180 and has to be half of that. All right, down here talks about opposite angles of a quadrilateral inscribed. An inscribed quadrilateral has to have vertices on the circle. So I'll draw one like this. I should use a different color here. So I want you to think of this as kind of two different inscribed angles. So if you don't understand what I'm going to talk about right now, I'm just going to tell you at the end. But in any event, again, I have this green inscribed angle. That makes this portion of the whole circle. Notice the blue inscribed angle makes this portion. Well, if I put those two portions together, it makes a whole circle, and a whole circle is 360 degrees. Well, if these inscribed angles are half, that means that this and this make 360 degrees of arc, so it has to be half of that, or 180. So that means opposite angles of a inscribed quadrilateral are always supplementary, which means they add up to 180 degrees, always and forever. That's because their arcs are 360. Let's see. Example problems. All right, so down here, basic problem here, I have a 36-degree inscribed angle because the vertex is on the circle. He wants me to figure out the measure of arc AC, which is this arc right here. And again, just use the relationship, which is I need to double this to get the arc measurement. So I do 360 or 36 times 2, and that's what, 72? So this is a 72-degree arc. Over here at number 2, now I know the arc measurement is 61. I think it's a 61. That's a 62-degree arc, so the angle is going to have to be half of that, which is what, 31? Down here, I want to find this angle right here. In order to do that, I have to figure out how big this arc is. Well, I have all the arcs of a circle are 360. I have these two, this one's 120 and this one's 140. So I'd probably add those together. And that is what, 260? So if that's 260 degrees, this remaining arc, which is the rest of the circle, would be 360 minus that, which is 100. Well, the inscribed angle has to be half of that arc, so it's got to be 50. Over here, I'm looking for the measure of arc MP. MP is this arc right here. So that's a 31-degree inscribed angle. I'm assuming that PN is going to be a diameter here, which means I have two semicircles. So this would be double that, which is 62. So I just doubled the 31 to get to 62. This is looking like a semicircle to me, or 180 degrees. So I do 180 minus 62. That's 8, take away 1, so that's 118. So that arc is 118 degrees. Down here, it wants me to use some algebra with these problems. It wants me to figure out how big W is. Let's see, the measure of W is pretty easy because it's going to be the same as this inscribed angle over here. So these are inscribed angles that make the same arc, ZY. So I know X is 22 degrees, which means this arc is 44 degrees because it's an inscribed angle. That's the arc, so it doubled it, which means that W also has to be 22 degrees just like X because it makes the same 44-degree arc. Measure of angle Y is going to be a little bit harder. I notice that Z and Y, Z makes this arc, so does Y, which means they have to be equal to each other. So I can take their measurements, 3x minus 23, and set it equal to 2x plus 2. Because these have to be congruent because they make the same arc. So then I'd use a little bit of algebra here. That means x is equal to 25. But it wants me to figure out how big y is. Well, I'll just take my newly found 25 and I'd probably plug it in there. So 2 times 25 is 50, plus 2 is 52 degrees. So that's how big y is. So that's how you do that one. More problems down here on the next page. Wants me to find the value of x. Notice that dot there, that's letting me know that's a diameter. So that means this inscribed angle is making a semicircle right here at 180. So this has to be a 90-degree angle right there. So then I can use triangle sum theorem. The 3 angles of a triangle have to add up to 180. So the one angle is 90, I just found that out. The one angle is x plus 12. And then the other angle is x, which is what I'm looking for. They're the 3 angles of a triangle, so they add up to 180. So that would mean 2x plus 102 is equal to 180. Subtract 102, so what's that, 78? So then I divide that by 2, what is that, 39? So x is equal to 39. Then it wants me to figure out what w is. Well, I know what x is now. X is 39, so all I have to do is add 39 and 12, and that'll give me the measure of angle W. So it's that 11 carry the 1, 51. So that's the way I do that one. Down here, and again, I notice I have a diameter on right there, so I know I have 2 semicircles in that case. And let's see, this has got to be inscribed angle making a 180-degree semicircle, so this again has to be 90 degrees right here. So again, I'd use triangle sum theorem on this one. 2x plus 90 plus 4x minus 6 is equal to 180. Solve it for x, plug it back in. I'm running out of time, so I'm going to skip down to number 5 and 6. Here I have an inscribed quadrilateral. Again, what you need to remember about this is opposite angles are going to be supplementary. So I'll start with R because I want me to find R. So that means this angle here is opposite this angle here. So that corollary says that these are always going to add up to 180. So then using triangle sum, I'd have 3x is equal to 105. And then I'd divide 105 by 3. And I get 35. So x is equal to 35. And I plug it in to figure out what the angles are. So basically 3 times x, or 3 times 35, is 105 degrees. To find s, again, I've just figured out what x is, so I just plug it back in. 2 times 35 is 70. So it wasn't that bad. But the important thing to remember here is opposite angles add up to 180. You could even have done 110 plus 2x. And they also equal 180 degrees. So then you have 2x is equal to 70, x is equal to 35. So it didn't matter which pair of opposite angles you used, you still ended up with the same value of x, and then you could use those to find the missing angles. So you have some homework problems like these tonight. You can turn those in. If you have any questions, show up to office hours, or you can shoot me an email. Either one will work. All right, let me know if you have any questions. Good luck.